we got this physics problem here. It has to do with forces and friction on a system. It says a freight train consists of two 8.0 times 10 to the 5th kilogram engines and 45 cars with average masses of 5.50 times 10 to the 5th kilograms. For part A, it says, what force must each engine exert backward on the track to accelerate the train at the rate of 5.0 times 10 to the negative 2 meters per second squared, if the friction force on the system is 7.50 times 10 to the 5th newtons. Assuming the engines exert identical forces, this is not a large frictional force for such a massive system. Well, yeah, of course, trains go easily. So let's think about this for a second. The wheel turns and pushes force back on it to be able to move forward. So we got to draw a diagram first with our X and Y axis. We got our trains, cars, and our engines. So we had our two engines that we put in there, and then we just only drew two cars, but we know there's 45 of them total, and we took that information from the problem. The same with the acceleration, we noted that down also. But since we're dealing with forces, we want to do, I also noted that information down there, the vectors and the direction the forces are going. So since we're dealing with forces, we have to draw a free body diagram. A free body diagram has the X and Y axis, and basically we're just using it, to find out about the forces. It helps us build a picture. So we're going to use a circle for our train and add the different forces. See, we have the force of gravity, which we note is like the mass times gravity, the normal force, which is equal and opposite to it. So the train's not going to be flying off. And since that's the case, we're going to ignore the Y direction. And then, of course, we have the force of friction on the system and then the force forward. So for part A, using the given information, we can obtain our total mass of the system, because we know how much the two engines weigh, or their mass. That's not weight, and then the cars. So if we know that the net force, like on a system, F equals ma, Newton's second law, that the mass total is going to be the 45 cars times the mass given, right? Plus the two engines times the mass given for that. And then that, at least now we got some more information, so we're going to be building this problem up quite a bit. Now let's think about this. The engines make the train move forward with acceleration A, which is given in the problem. So if we sum the forces, which is the net force by the engine, which is given by two of the engines, because remember it says there are two, and the friction force is in the opposite direction of the force of the engines. So we know the mass times the acceleration is equal to 2 times the force of the engines minus the force of friction. And that the net force, or the total force on the system, is equal to ma. So that means that the force of two engines minus the force of friction is ma. So that's how they're related. So we're going to rewrite the equation to find the force of just one car, because we're going to need that information to solve part B of the problem. If we substitute in our values from that we obtained that we had solved for like the total mass, and we substitute it in, we find the net force on one car is 1.03 times 10 to the 6 newtons, which is still, that's quite a bit of force for just one car. So for part B, it's asking us, what is the force on the coupling between the 37th and 38 cars? What is the force that it exerts on each other, assuming the cars have the same mass and that the friction is evenly distributed among all the cars and the engines? So, if it's by all the cars and the engines, maybe we should draw a diagram again to kind of give us a better picture of this. Of course, we draw our coordinate axes first. This diagram's a little bit different than the first one, and we can see we have the coupling right here in the middle of the two cars, and then we still have the engines. So we know that the total mass and that there's 45 cars total, and then there's 2 engines total. But it wants to know what is the force between the 37 and 38 cars. So if there's 45 cars total and there's 8, like let's say remaining at the end, we know that there's 37, or 45 minus 37 is 8 cars. That's how we get that information. So since we're dealing with forces again, we're going to deal with a free body diagram. Because we're trying to figure out the force on the coupling. So a lot of other stuff we can kind of, it's just there in the problem to try to, I don't know, confuse us, or it's just not there. So we're going to draw a free body diagram, and our little square box is going to represent the force or the coupling. And then we have, of course, the X and Y axis. And we're going to appropriately label our forces. So we have the acceleration, we have the force of gravity, the mg, the force of the coupling from 8 cars only. So there's 8 cars in the back, right? And then we're trying to find the force on the coupling, which is connected to the 37 other cars. So we know, what do we know about friction force? We know that the friction force is equal to mu static mg, which is mass times gravity. And if we have all that information, let's think about this a little bit more, okay? The friction force is a ratio, or it's a proportional to the mass. So the 37th or the 38th car and the ones ahead are being pulled by the 2 engines, and the 37th car and the remaining cars behind are being basically dragged along by the coupling or cable or whatever it is. The force is proportional to a fraction of the mass. So what a fraction? So even though that it's all distributed evenly amongst the cars, even if we're taking a ratio, it's still going to be the same because they said it's distributed evenly. So that's something important to think about. And recall that we did calculate the total mass in part A. So we know how much it is. So we're just taking a fraction of which the 8 cars are. Which the force on 8 cars is equal to the mu static in 8 massive 8 cars. Instead of just mg, we're just doing 8 cars because it's a fractional part of it. And then times gravity. And we know that the friction force is given by the total friction force is the mu static times mass times gravity in a system. So to get the ratio that we're looking for, you got to divide the friction force of 8 cars by the total friction. And mu and g are going to cancel, and you multiply both sides by the total friction force by 8 engines and the cars. And it cancels out. And then we're left with the force of 8 cars is equal to the mass of 8 cars over the total mass multiplied by the total force of friction on the system, which is given in the problem, the 7.50 times 10 to the 5th. So if we're doing this, we need to find the force acting on the coupling between the cars. So we have to sum the forces. So the force of the coupling minus the net force on 8 cars is equal to the mass times the acceleration. F equals ma. So the force of, as I said, the force on the coupling minus the force of the 8 cars, which we had calculated previously, equals 8 ma, or F equals ma. So the value we obtained previously, the force of 8 cars is equal to 8 times the mass of the cars, divided by the total mass, times the total friction force on the system. Our substituted and rearranged equation, that means the force of coupling is equal to the mass divided by the total mass times the friction force plus the mass of 8 times the acceleration. So we have this manipulated and rearranged equation. To find the force on the coupling, we're simply summing the forces. Okay, so we have the force 8 MCA plus the force of 8 cars, 8 times the mass of the cars divided by the total mass times the total friction force. So we're basically summing the forces in the x direction. And if we substitute our previously obtained values, we're gonna plug in all the numbers we have from the problem, the 8 times 5.5 times 10 to the 5th kilograms over the total mass times the total friction force on the system, which was given in the problem. And then we're summing the forces, 8 times 5.5 times 10 to the 5th kilograms times the acceleration. And the force on the coupling is 3.4 times 10 to the 5th newtons. That's quite a bit. Like, if you think about it, like, pulling on each other, like, how strong that would be, it would be strong enough to, like, break someone in half. So, we did it.